Here we're going to look at how to determine the earliest starting time and earliest finishing time for a network as part of critical path analysis. So here we have a familiar example that we covered in a previous video of putting on socks, shoes, pants and belt. And I've just drawn it here. And now we're going to go through this picture and determine some interesting properties about these activities. In particular, we're going to look at the earliest starting time of each activity, which is defined to be the earliest time that all the prerequisites of that activity can be completed, and of course that activity can then be started. And we're also going to look at the earliest finishing time, which is the earliest time that activity can be finished, but in reality we really just look at the earliest starting time and then add the time it takes to actually do that activity, and that becomes the earliest time it can be finished. So it's this one that we really look at, and this one's kind of a secondary thing. You go through in your critical path analysis, when you have a network diagram like this, the first thing you do is draw boxes on top of each of the vertices. So here I'm going to draw two boxes, over here, over here, over here, and over here. This is traditional. You only use one box for what's called the forward scan that determines the earliest starting time of the activities, and you traditionally put it here. So this EST is what we're going to put in this box, and we're going to use the second box a little bit later. So the earliest starting time of activity A. Remember, activity A has no prerequisites. You can tell that diagrammatically because it's connected to the start vertex, and so A can be started immediately. Similarly, B can be started immediately, and we always have a 0 there above the start vertex, indicating that A and B can start immediately. It takes 0 time to do 0 prerequisites. Let's think about this. Remember, the vertex represents the completion, the achievement of all activities pointing into that vertex. And so how long does it take to achieve all the prerequisites here? Well, the only achievement this is B represents is B, and B can be done in time 3. So it only takes 3 to do. We can start it immediately. So the earliest you can achieve this vertex here is 3. This one is a little bit more interesting. Now this is a dummy edge, just indicating that just kind of extending B up here. To achieve this vertex, we need to have completed B, and we need to have completed A. Remember, the vertex represents the achievement of all things pointing into it. So how soon can we be at this vertex? We can do this branch in time 1, and we can do this branch here in 3 plus 0, so time 3. But we can only get all of them after time 3. You need to have all of them present, and so you take the maximum of all the times leading into it. This one over here, well, technically it's the maximum of all the earliest finishing times of the activities pointing into that vertex. So let's have a look at this one. How soon can activity? Sorry, not 0. That's a 3. So this is the most interesting one. How soon can we be finished to this branch and finish this branch? Well, on this branch it's 3. We start at time 3. It takes 2 to do, so the earliest we can be finished is at time 3 plus 2, which is 5. And on this branch, the earliest it can be finished is 3 plus 1, which is 4. But we have to take the biggest, because that's the only time, because that's the time when both will be finished, the earliest time when both will be finished. So we always take the maximum, and the earliest finishing time, or the earliest starting time here is 5. Incidentally, this number is the smallest amount of time it takes to complete the whole project. Imagine that you've just performed a forward scan on this network and you've discovered the earliest starting times at each of these vertices, and you discovered that the earliest you can complete this whole project is in 5 time units. And you turn to your boss and say, "Hey boss, I can do the whole thing in 5 time units." Your boss turns back to you and says, "That's good. You have exactly 5 time units to complete the whole project." Now, Some activities here need to go like clockwork. No delay is acceptable whatsoever. And some of the activities can be delayed. And we'll see more about those kinds of things in a moment. But before we get there, we need to talk about finishing times. So the latest finishing time is the latest time that the activity can be completed. And the latest starting time is the latest time that you can achieve all the prerequisites of those activities and then have enough time to actually do that activity. We're going to determine the latest finishing times by a procedure called the backwards scan. We're going to do that now. And along the way, we're going to find out the latest starting times by just taking the finishing times and subtracting the amount of time it takes to actually do the activity. So, you've just discovered that it takes 5 time units to do this. Well, guess what? You just copy that over, and that's the latest finishing time. So that's what these other boxes are for, and that's the latest finishing time. And it means the latest finishing time of C and D, i.e. of all the activities pointing into that vertex. So activity C can finish at this time at the latest, and activity D can finish at this time at the latest. What does that mean for this thing? Well, we look at how late you can achieve this vertex and still get the project done at time 5. And the answer is, well, if you've done this at time 3, you have exactly 2 time units to do C, and you can still hit this by 5. So you put a 3 here. This one is but I might just mention, that is to say you put the latest starting time of activity C in this box. This one is a little bit more interesting because it has 2 things pointing into it. Coming down here, the latest starting time of activity D is just 5 minus 1, which is 4. But if you were to put a 4 here, then you wouldn't be able to get here by time 3. What you need to do is consider the minimum of all the edges that are pointing out of that vertex, or the minimum LST of all the vertices that are pointing out of the vertex. So here we have activity D has an LST of time 4, and this dummy activity has an LST of time 3 minus 0, which is 3. To take the minimum would mean putting a 3 here. Now over here we have 2 edges to consider. The LST of activity A is 3 minus 1. That is to say, the latest you can start activity A and still finish this by time 3 is 2. Kind of makes sense. A only takes 1 time unit to do. You have to be done it by time 3, so you can sit there and twiddle your thumbs for the first 2 time units, do activity A in 1 time unit, and still be here and not delay the whole project. So LST of activity A, just that minus that is 2, but the LST of activity B is that minus that, which is 0, and we take the minimum, 0. As a sanity check for your project, you should always have double zeros at the start vertex. So if you've not got a 0 here, then you need to go back and just figure out where it went wrong. Let us continue with our example where you have a project and you've told your boss, hey boss, I can do my project in time 5, and your boss has said, hey great, you have exactly that much time to do your project, and so you're under the pump to get this certain aspects of this thing done like clockwork. And there'll be other aspects of this project which can be delayed, like in activity A, where you can sit there and twiddle your thumbs for 2 minutes and it doesn't matter because you've got 3 whole time units to do it and it only takes 1 time unit. We make this more formal now by introducing the concept of float time and the critical path itself. Now, the float time of an activity is the difference in the start times. We already know how to compute the LST and EST. We have all this information on the diagram. The best way to compute the float times is just to use the information that you have on the board and take for activity A. Remember, this is the EST of A. This number on the right is the LFT of A, and this is the duration. The fastest and easiest and therefore best way to compute the float time is just to take that minus that minus that. So that is to say, use this formula here, LFT minus duration minus EST. And this is nice because it involves all the things that you've got on the board. You don't have to think about anything, you just do that, that, that. So 3 minus 1 minus 0 is 2, the float time of 2, which we talked about earlier. Activity B, well, that minus that minus that. 3 minus 3 minus 0 is 0. Activity C, 5 minus 2 minus 3 is 0. And activity D, well, that's going to be 5 minus 1 minus 3, which is 1. And so float times are relatively easy to compute once you have all this information in front of you. And the critical path, and there'll always be at least one, there may be more than one, but at least one. The critical path is a path from start to finish that involves only these activities with float time of 0. So we might just put a little marker on the float times on the edges which have a float time of 0, and so we can see we can travel from here to here using only those ones. You can use the dummy edges, that's fine. So the critical path here is along here, then skip up there. It's a dummy edge, it doesn't do anything, doesn't take any time, and along here, and that's our critical path, B, C. Now let's do a more sophisticated example of finding the critical path using forward scanning and backward scanning. Now this is the proper way to do a critical path analysis. It is not the way you would do a critical path analysis question in a multiple choice exam. It takes way too long to do this process for say 1 or 2 marks. So this is the full and proper director's cut method. It is not what I recommend you do in a multiple choice exam. But let us go forth and actually do the procedure. Remember, you put boxes above all the vertices, like so. And you go through and you perform the forward scan to determine all the ESTs of these activities. You give this vertex here a 0, representing an EST of 0 for activities A, B, and C. Okay, the first thing we do is look at how soon we can achieve this vertex. How soon can the prerequisites of E be achieved? Well, that's just 0 plus 2, so that's 2. B, how soon can we achieve this? Well, we need to know how soon we can be done with this line and how soon we can be done with this line, and we don't know that one quite yet. So let's just hold off on that one for a moment. This line, there's only one edge incoming to this vertex, so the soonest you can achieve this edge is 0 plus 5, which is 5. Now we can come back here. We know how long it takes to achieve this edge, that's just 0 plus 1, and we know how long it takes to achieve this edge, just 0 plus 5, and in order to achieve this edge, the earliest you can possibly do it is at time 5. You need both of these things to be achieved, and so the earliest is you just take the maximum there and put a 5 down. Good, then you just proceed through. This one here can be achieved at time 5. This one here, that's just, there's one thing incoming, so it's just 7. This one, 3 things incoming. Now, if it's helpful, imagine that your project is you're going on a road trip, you're waiting for 3 friends, and you want to know how soon can my 3 friends be here, ready for us to go on the road trip. Well, you need to know how soon each of these individual 3 friends can get there, and you need to wait as long as it takes for all 3 to be there before you can proceed on your trip. So down here we have 5. Well, this person's going to leave at time 5. It takes 2 to get there, so this arrow can be done at time 7 at the earliest. This one here can be done at time 9 at the earliest, and this one at time 8 at the earliest. And you have to wait for all 3 before you can proceed. And so all 3, the earliest all 3 can be there is at time 9, i.e. the maximum. This one here, that's going to be 11 or 16, we take the maximum. And this one, well, there's just one thing there, 18. Great, we've done our, I'll just clean that up a bit. We've done our forward scan. We've determined all the ESTs in our project, and now we need to find my purple pen It was there all along. Now we need to find the LFTs. So imagine you've just discovered that this whole thing can be done in time 18, and you say to your boss, "Hey boss, I can do it all in 18." Your boss says, "Great, do it in that time." And then you're under the pump. 18 is the latest time you can finish activity L, and that means you better have achieved all its prerequisites by time 18 minus 2, which is 16. Otherwise, you won't be able to do that. This one. What's the latest you can achieve this vertex and still then go on to do activity K, which takes time 7? Well, that's going to be 16 minus 7, which is 9. This one over here, you need to look at two things. What's the latest time you can achieve this and still have enough time to do 6 and get here by 16? Well, that's going to be just 16 minus 6, which is 10. And on this branch, what's the latest time you can achieve this and still be done, what's the latest time you can achieve this to then do activity H and be finished by time 9? Well, that's 7. And so you have to take the minimum. Down here, this is just going to be 9 minus 1. There's only one thing to consider, so you just put an 8 there. This one here, again, only one thing to consider. 9 minus 4 is 5. 7 minus 3 is, let's see now, 4. This one, there's two things to consider. 8 minus 2 is 6. 5 minus 0 is 5. You take the minimum, 5. And now there's three things to consider. 4 minus 2 or 5 minus 1. So 2, 4 or 0. We get 0. And that makes sense. We were hoping to get a 0 there, and we did. Great. Now let's go forth and just mark off which of these activities has a float time of 0. Now I'll remind you, you can compute the float time with all the information we have here. You just take, for activity L for example, latest finishing time minus wait minus latest starting time. So 18 minus 2 minus 16 is 0. So the float time is 0. So this thing is going to be on our critical path. Just kind of underline it like that. This one, activity K, its float time is 16 minus 7 minus 9, which is 0. So that's on our critical path. This one, that's float time is 16 minus 6 minus 7. So that's a float time of 3, not on our critical path. This one, activity I, has a float time of, well, to be honest with you, for ones where these things are not equal, you don't need to consider those. You only need to consider the ones where the float times are equal. But those things being equal does not guarantee the float that it is on the critical path. You need to look a little bit further than that. You need to look at the float times. But you don't really need to look at the float time of this. It's not going to be on the critical path, simply because those numbers are different. Okay, so this one, this activity 9 of activity F, 9 minus 4 minus 5 is 0, so this is on the critical path. Activity D, 5 minus 0 minus 5, critical path. Activity B, 5 minus 1 minus 0 is 4. Activity B has a float time of 4, not on the critical path. You can twiddle your thumbs for 4 whole time units, do activity B, still make it there by time 5. Definitely not on the critical path. Activity C, 5 minus 5 minus 0 is 0, so that's got a float time of 0, and that's on the critical path. And so you can see, by performing the forward scan, then the backward scan, and then looking at the float times, we determine the critical path.